Buenas tardes! Our subject today is generalized linear Diophantine equations. We write it down with integers, we write it down with polynomials. We use the 104 example with complex numbers with integer coefficients. Now we're gonna generalize to the last possible thing except polynomials on several variables. What is an integral domain? It is a commutative ring. A ring has a sum and a product. An integral domain has an identity 1 and has 0. If AB is equal to 0, then A is 0 or B is 0. So there are no different from 0 divisors. In an integral domain divided by an ideal with a delta, that's where we're gonna work. A delta has already been explained. An ideal I is a subring I of R. We are working in R, space R, such that if small r is in R, x is in I, then the product Rx and XR are in I. So there are several examples of ideals of R. The center of R is an ideal. 0 alone is a trivial ideal of R. The whole R is a trivial ideal of R. The space generated by A of R is an ideal of R. It is one constant times everybody in R, like 7z, 3z, okay? A vector times lambda is a straight line, and the plane A1, A2 is an ideal of R, and a hyperplane A1, AN is an ideal of R. A ring generated by constant of R times A1, constant of R times AN. Everything summed. F is a function of F R to the ring S. It is a ring homomorphism if f of A plus B is equal to f of A plus f of B, and f of AB is equal to f of A times f of B for all A and B in the ring. Another example, the kernel of f, the roots of f of x, is an ideal of R. Everything must be demonstrated, proved. It is in Hungerford. Hungerford says also that the intersection over a family of ideals of R is an ideal of R. Hungerford defines the principal ideal generated by A such that it consists of all elements of this form: R1 A plus A R2 plus alpha A plus the sum of R's A R's from I equals to 1 to beta, from 1 to beta. Então we have R1, R2, R3, R4, Ri. In R and alpha, beta are integers. We multiply by an integer with some integer indexes, and after that amazing theorem or definition, we're going to define our new space M of quaternions. What is a quaternion? AI, BJ, CQ plus a real. In matrix form, we have S plus Ti, S minus Ti, U plus Vi minus U plus Vi, a 2 by 2 matrix with STUV in Z integers. Our delta of quaternions is S2 plus T2 plus U squared plus V squared. Remembering that if A and B are in M and are not 0, and therefore delta of A is less than or equals to delta of A times B. Whenever A and B are in M, B is not 0, we have a quotient and a remainder in M by the Euclidean division algorithm of centuries before Christ. A is equal to BQ plus R. The remainder is 0, or the delta of the remainder is less than the delta of the divisor. Now we're going to Zm. It's Z multiplied by M. A single number Z multiplied by the whole M for integers. Multiplied by 11, 13, 17, 14. Dividing the ring by the ideal, we have the quotient ring. Another ring, we will denote the elements by xz. They are equals to a single point x plus a single point z multiplied by the whole space M for a single x in M. This space is called MZ. It is analogous of z over 3z equals to z3. The three elements 0, 1, 2 plus 3z. The multiples of 3, the multiples of 3 plus 1, the multiples of 3 plus 2. Z3, MZ. M over Zm, Z over 3z. Now we're going to solve an equation in the quotient ring. AZ times XZ plus BZ times YZ is equal to the greatest common divisor of XZ and YZ. This equation will always have solution, right? Except 0, 1s, it will have solution if we have a delta 2 from MZ minus 0z to z plus. We have a delta in the original space and we need a delta in the quotient ring. If we were at z7, we might choose the representative 0, 1, 2, 3, 4, 5, 6 in N. And we would find a quotient and the remainder at z7 like this. Divide 5 by 3. We have a quotient 1 and the remainder 2. So we should 5 plus 7, 12. 12 divided by 3 is 1. Plus 7, 8. Plus the remainder 2. Plus 7, 9. Okay? Remembering that the greatest common divisor is a set. If we have a single GCD of xy, we have all the units of R. We have the set of greatest common divisor multiplying all the units by one GCD. A unit is a divisor of 1. U is a number such that there exists W in R such that the product UW is 1 equals to abelian W times U. So they are inverted. W is the inverse of U. So our equation might be simplified. In this case, not in every case. In the case we're using an ideal generated by a principal ideal generated by A, the equation becomes ax plus by equals to GCD xy plus CZ. Why? Because A plus Z, X plus Z, B plus Z, Y plus Z, GCD plus Z. All we need is to add a constant times Z in a side and solve the equation A x1 plus B x2 minus C x3 equals to GCD of G x1, x2, x3. We're ready to solve it. This might have solution. The precedent equations might not have solutions. So this equation have a solution. If x1 is generated by 41, 43, the primes 47 and 53, if x2 is a point generated by 23, 29, 31 and 37, if x3 is our last z generated by 11, 13, 17 and 19, you already know how to solve. Just repeating. Who is y1? Ax1 plus bx2. So we're going to have a1 minus cx3 equals to GCD. And we have a single solution for y1 of lambda and x3 of lambda. We have an ordinary solution z0, z3. And whenever we add c to y1, we have to add 1 to x3. Right? Now we're going to turn back to the definition of y1. Ax1 plus bx2 is equal to y1 is equal to z0 plus c lambda. It has an ordinary solution to x1 and x2. If z1 is a solution and z2 is a solution, then z1 plus bme is a solution. z2 minus a is a solution. Whenever we add b to x1, we have to subtract a to x2 because ab minus ba is equal to 0. Therefore, the everlasting solution is a y x y z from lambda and me. z1 plus b me, z2 minus a me, and z3 plus lambda. Out of charity, there is no salvation at all. If you know how to generalize this, send to me, please.